Hello everyone, welcome to the video lecture series on quantum computing. Quantum computing is a very interesting and very ambitious subject in theoretical computer science, and it's getting really popular these days considering the fact that we are dealing with enormous amount of information and large data in communication. So I'm planning to prepare a video lecture series on quantum computing covering a one semester course. We will have 6 chapters. We'll start with an introduction, and then we'll move on to basic quantum theory, and then we will talk about quantum teleportation and quantum algorithms, and then we will move on to quantum error correction, and then finally we will cover models of computation and quantum complexity. I've tried to include all standard topics that are usually taught in a standard quantum computing course. So I tried to select most standard subject as much as possible. Now, one of the requirements for this course is some level of linear algebra. So basic understanding of linear algebra is desired. Okay, it's one of the requirements. You don't have to know anything about quantum mechanics. I mean, we will already cover that in chapter 2, so you don't have to worry if you haven't taken a course in quantum mechanics. But I will assume that you're familiar with linear algebraic notions such as vector spaces, matrices, inner products, and so forth. But we will cover essential details. Okay, so quantum computing is a new paradigm for computation. It relies on quantum mechanics, which is a deeply strange theory, which challenges our traditional notion in physical reality, in classical physics, that we know of the macroscale world. Quantum mechanics is inherently probabilistic, and it forbids us from measuring certain kinds of physical quantities. For example, due to Heisenberg's uncertainty principle, there is no way that we can know for certain both the momentum and the position of a subatomic particle. Asking such questions are forbidden. If a subatomic particle, say, has traveled from point A to point B, then we may not actually know which path it followed. Okay, but despite all the pitfalls, quantum mechanics has been very successful in explaining the physical reality, conductivity, chemical reactions, and so on. And if we turn to computation, now classical computation has served us pretty well for many different purposes. Okay, and these classical computations mostly relied on rules of classical physics, or in other words, Newtonian physics. Okay, but as we all know, with the scientific revolution in the early 20th century, with seminal works of Einstein, Schrödinger, Dirac, Bohr, and many other influential scientists, a new kind of physics appeared. So this tells us that, well, maybe we should change our computational paradigm so as to make it compatible with the new with the new physics, okay, quantum physics. So quantum computing is a type of natural computing which uses subatomic matter and quantum mechanical principles, okay, that we will explain later, such as the superposition principle, interferences, and entanglement principles. So a quantum computation makes use of these properties. Okay, so these are quantum mechanical properties which are not present in any classical computation. We can simulate maybe superposition and interference, but especially entanglement is a very inherent property of quantum systems. And some problems can be solved more efficiently by quantum algorithms compared to classical algorithms. Okay, but we should note beforehand that quantum computers do not solve problems that are unsolvable by classical computers. Okay, so essentially, in theory, quantum computers are equal in computational power to classical computers. They solve the same class of problems, okay? But some problems can be solved more efficiently in quantum computers, such as the integer factorization problem, unordered search problem, discrete logarithms, hidden subgroup problem, which is a problem in algebra. We will mention that later. That is not to say that classical computers cannot solve these problems. Okay, it's just that some problems are solved more efficiently by quantum computers. Okay, but in theory, classical computers and quantum computers are of equal power. Okay. Now, I will use the standard notation that are used in many other textbooks. Occasionally, we will refer to other works. Okay. Now, I strongly recommend Nielsen's book, Chuang and Nielsen, Quantum Computation and Quantum Information. Okay. And also Janowski and Manucci. Quantum Computing for Computer Scientists. Okay, another book. And another book would be by Gruska, Quantum Computing. So these are some of the textbooks that I would strongly recommend the viewer. Okay, so I'm going to assume some basic familiarity with linear algebraic notions, as I said. I'm also going to assume that that you're familiar with high school trigonometry and complex numbers. I'm not going to assume any background on quantum mechanics. Okay, we will cover that in chapter 2. But first, let me talk about what classical deterministic systems are. Okay, so classical deterministic systems. So I also have the lecture notes, okay, as a supporting document and as a supporting material. Um, so if you'd like to have that, just contact me and I'll try to help. Okay, so classical deterministic systems are used in classical physics and in daily life. Um, a One of the most boring classical system, deterministic system, would be a toss of coin, right? So imagine that we have a system, okay, and this coin is, let's say that it's determined. It behaves in a deterministic way. So if I have tails, and if I know that in the next round I get heads, okay, and if I have heads, let's say I get tails in the next round, okay, so it behaves like head, tails, and so on. Now this is a deterministic system because at any stage t, I can determine the state of the system at stage t plus 1 solely by looking at the state of the previous stage. Okay, so I can determine the next stage, the state of the next stage, by looking at the state of the previous stage. Okay, or maybe I could have a die. Okay, just one die. Okay. So imagine I just roll the die, and whatever I get at stage n, the value of the next stage will be, let's say, n plus 1, n plus 1, okay? Mod 6, of course, okay? Or, yeah, mod 6. So if I get a 5 at stage t, I know that the value I get at stage t plus 1 will be 6. If I get 6, then in the next round I will get 1. Okay. So these are examples to classical deterministic systems. Okay. Now, a very nice example was given in Janowski's book, Child Marbles. Okay. A marble system can be imagined like a graph, some marbles placed on the vertices of a graph. So imagine I have some vertices, vertex number 0, vertex number 1, vertex number 2, vertex number 3, 4, 5. And imagine at vertex number 0 I have maybe 6 marbles. Okay, and here I have 2 marbles, let's say. Here I have 1 marble. At vertex 5, let's say I have 5 marbles. Here I have 3 marbles. And let's say we have 10 marbles on vertex 5. Now this is a state of a system, right? And the state of the system can be represented by a column vector. Okay. The first row will denote the number of vertices at vertex 0, which is 6. And then I have 2 marbles at vertex 1. Vertex 2 has 1 marble. Vertex 3 has 5 marbles. 3, 10. Right. So this denotes the state of this marble system. Okay. Occasionally, we may use the row matrix form, and in that case, we may also denote this as mt transpose of m, which you know from linear algebra, and this can be also represented by a row vector, 6, 2, 1, 5, 3, 10. Okay. So this is the transpose of M. Okay, so Mij transpose means Mji. Okay. All right. So now that we denoted the state of a system by a row vector, we're also interested in the dynamics of the system and how states change with time, okay, with discrete time intervals. Now we can represent the dynamics of a system by a directed graph. So let's say that if there's an arrow from vertex I to vertex j, then let's say that at one time click all the marbles on vertex I will move to vertex j. Okay. So assume that we have something along the lines as, so let's say vertex 0 goes to vertex 5, vertex 1 goes to 2, vertex 2 goes to 3, vertex 4, vertex 4 goes to 5, and 3, let's say it self-loops. Okay, so that means here all the marbles at vertex 0 go to vertex 5. Okay, now we can represent this dynamics with an adjacency matrix. Okay. All right. So actually, let me denote this state vector by x. Okay, because I want to denote the adjacency matrix with the letter m. All right. So the adjacency matrix is a 0, 1 matrix basically, and it shows the relations, the connectivity relations between the vertices. So this represents the connectivity relation of vertex 0. So vertex 0 was only connected to vertex number 5. So vertex 0 is not connected to itself. So we put 0. Vertex 0 is not connected to vertex 1. It's not connected to other vertices. It's only connected to vertex number 5, the last vertex. Okay, we have 6 vertices in total. So vertex 0 is only connected to vertex 5. Okay. And then the next column represents the connectivity of vertex number 1. Okay. Vertex 1 is only connected to vertex number 2. So we have 0, 0, 1, 0, 0, 0. Right. And then vertex number 2 is connected to vertex number 4. Okay, so we have 0, 0, 0, 0, 1, 0. Okay, and now we look at vertex number 3. 3 is connected to itself, it self-loops. So 0, 0, 0, 1, 0, 0. And vertex number 4 is connected to 5. And 5 is connected to, right, there's an arrow missing. I forgot to draw this. So vertex 5 is supposed to be connected to vertex number 2 in the example. So it's 0, 0, 1, 0, 0, 0. Right, so M denotes the adjacency matrix of this directed graph. Okay. Now, if we multiply M, okay, by the state X, what we get is the state of the next stage, right? So m multiplied by x gives us 0, 0, 12, 5, 1, 9, right? Let's call it y. So y describes the state of the next stage. Okay, we're talking about discrete stages. So x is the state of the system at stage S, and y is the state of the system at stage S plus 1. Now, if we apply m on y again, we get the state of the next stage, right? Okay, so m is a way of describing how the state of the system changes. And in fact, finite dimensional quantum systems work in the same manner. So we apply a matrix n many times consecutively on the state to see how the system changes after n many stages. But we said that quantum systems are not deterministic, they are probabilistic. So let's turn our attention to probabilistic systems. Let's consider the same marble example, but let's instead deal with a single marble. Okay, so suppose that we have a three vertex graph. Okay, let's say vertex number 0, vertex number 1, vertex number 2. All right, so now in a typical three vertex graph system, a probabilistic state would look something like, maybe 1 over 5, 3 over 10, and 1 over 2. Okay. Now this will correspond to the fact that, now we assume that there is only single marble in the system, okay, either in 0 or 1 or on vertex number 2. And this state, x tells us that that there is 1 over 5 chance that the marble is on vertex 0, 3 over 10 chance on vertex 1, and 1 over 2 chance on vertex 2. So since we want to deal with normalized systems, because the summation of the probabilities must add up to 1, okay, we assume that we are working in normalized systems. The marble must be somewhere in the system, so the sum of the probabilities is equal to 1. Okay. Now we can also generalize the dynamics of the system to a probabilistic system. Instead of having exactly one edge leaving each vertex, we can allow multiple edges. Okay. With the condition, of course, that the sum of the probabilities of outgoing and incoming edges add up to 1. So maybe we could have something like, so if the marble is on vertex 0, then let's say with probability 1 over 3, it goes to vertex number 1. Okay. And with probability 2 over 3, let's say it goes to vertex number 2. Okay. And if the vertex if the marble is on vertex 1, let's say with 50-50 probability, with 1 over 2 probability, it goes to itself. And with 1 over 3 probability, it goes to vertex number 2. With 1 over 6 probability, let's say it goes to vertex number 0. Okay. And if the marble is on vertex number 2, let's say that with probability 1 over 6, it goes to 1. With probability 5, over 6, it goes to vertex number 0. The matrix representation of this dynamics can be represented by the matrix 0, 1 over 3, 2 over 3, 1 over 6, 1 over 2, 1 over 3. Here we have 5 over 6, 1 over 6, 0. Okay. And if we suppose, so let's suppose that our initial state is, let's say 1 over 6, 1 over 6, 2 over 3. Then if we apply m on x, we get 21 over 36, 9 over 36, 6 over 36. So this is the state of the next stage, okay? And the normalization is preserved. Still, the sum of the probabilities is equal to 1. So quantum systems, they evolve in the same manner, okay? They are probabilistic. Manipulating the system will correspond to multiplying this state by a matrix. Okay, so each computational step will correspond to one matrix transformation. So this is how quantum systems will evolve. All right, so now that we've discussed classical, deterministic, and probabilistic systems, let's now consider quantum systems. Now, quantum systems are probabilistic systems, but one of the first observations about quantum systems was observed by Thomas Young with his famous double-slit experiments. Double-slit experiment. So this was around early 19th century. Thomas Young. So Thomas Young conducted the famous double-slit experiment. So this is a physics experiment which explained the concept of wave-particle duality. Which gave us hints regarding the behavior of matter at the subatomic level. So this experiment also helped us to understand the physics of the microscopic world, because subatomic matters are neither particles nor waves, but they behave in their own quantum mechanical way. So the experiment shows us that subatomic particles behave sometimes like a microscale particle and sometimes like a wave. So, but this behavior has dramatic effects. So in this experiment we have a source emitting light or electrons. Okay, so we have a source This is our source emitting maybe light or electrons, or maybe even macroscale objects like paintballs or bullets. Okay, so we have in front of the source we have a panel on which there are two slits. So this is slit 1, this is slit 2. Okay, and then we have a panel on which we can measure the energy level of the particle, okay, on any point of the panel. All right. Now let's suppose that our source is throwing maybe paintballs. Okay, so we're throwing macroscale objects. Now what happens if the first slit is open but the second slit is closed? Now what's going to happen is, so let me erase this. What's going to happen is that if slit 2 is closed and if only slit 1 is opened, we have something like the probability distribution will look something like this, right? Because the probability of the paintball hitting the position aligned with the slit is more likely than the other parts of the panel. It will more likely hit the middle rather than the sides, right? So let's call this P1x, okay? The probability distribution at position x. What about if slit 2 is open? Well, it will behave exactly as the same as earlier. P2x, right? So nothing fancy here. If both slits are open and if we are throwing paintballs from the source, then the probability distribution will be P1x plus P2x, right? So this is the behavior of a macroscale particle. Macroscale particle. All right, so now what happens if we emit light? Now if only slit 1 is open and slit 2 is closed, then it behaves exactly like a macroscale particle, right? The probability distribution will be like this, same as earlier, okay? Nothing surprising really. The light that hits in the middle parts aligned with the slit will be more intense than the other parts, okay? So the sides will be more dimmed down. Okay, but what happens if we open both slits? Now what happens now is that now that we have waves coming from slit 1 and slit 2. Now what happens here now is that it's going to form an interference pattern like this. Okay, it's going to be more intense in the middle parts. The intensity will be lower compared to the middle part, but it's going to form an interference pattern like this because the level of the light, the intensity of the light will be higher here and lower here. It will be again higher here, but lower here. So in some parts, the intensity will be higher, and in some parts, the intensity of light will be lower. This is because of the fact that when two waves travel, okay, when two slits are opened, they will interfere with each other. So in some parts of interference, their energies will cancel each other. So these will be the parts where the energies of the waves cancel each other. Okay, but in some parts, their energies will reinforce each other. So these will be the parts where they reinforce each other. So we have an interference pattern, and this is not we cannot denote this probability distribution just by P1x plus P2x, but let's say this is P12x. Okay, this is not equal to P1x plus P2x. Alright, so this is the behavior of wave. And this is the behavior of the macroscale particle on the left-hand side. Now, what happens if we shoot electrons or photons one at a time? Let's assume that the intensity of the source is sufficiently low that it emits the photons or electrons as discrete particles once in every second, let's say. So imagine that we are shooting electrons one by one, and let's assume that only one of the slits is opened. Let's say only slit 1 is opened. Now, there's nothing surprising here. If only one of the slits is open, then we have a similar probability distribution. So we either get P1x or P2x if only one slit is open. If both slits are open, even though we're shooting particles, right, electron particles or photons, even if we're shooting particles, after a sufficient amount of time, we observe that it forms a wave-like interference pattern. So that's very interesting, because we're shooting particles, but it behaves like a wave. When both slits are open, after a sufficient amount of time, we observe the same interference pattern. So this is called the particle-wave or wave-particle duality. And it demonstrates that the physics at the subatomic level is a lot different than that of the macroscale level. And what's even strange is that as long as we do not observe the electron, it's going to form an interference pattern, okay? But if we put an observer next to either of the slits, and if we observe the subatomic particle, the photon or the electron, it's going to start behave like a macroscale particle, and it will lose its superposition property. Right? So that means if we don't observe electrons or photons, the photon or the electron actually passes from both slits. That's why it's forming the interference pattern. But if we measure the state of the system, if we measure the electron or the photon, it's going to lose its superposition property, and it's going to start behaving like a macroscale particle. So it's either going to pass from slit 1 or slit 2, but not both. So this is completely mysterious. But the property of the superposition property and the interference property and other quantum mechanical properties will bring enormous amount of power in computations. Okay, so now next is to look at, well, how do we mathematically define this? How do we mathematically define a framework for quantum computing? Okay, and this is what we will discuss next. So I'll see you in the next video.